Okay, I'm going to get started. Let me let you know a little bit about myself. I'm Karen Camp. I'm a teacher, educator, and technology consultant. I love to use technology to help students visualize and make math meaningful for them. GeoGebra is a wonderful platform to do this. And I'm going to go through several different activities that I have. They're all available, and you're going to get access to the activities as well as the Dropbox with all of the handouts if you decide you want to use paper handouts with your students. So don't necessarily try to follow along because everything I'm going through is going to be available to you at the end, not just the recording, but I'm going to give you links to the Dropbox. So let's get going. What is the action consequence reflection cycle? Action consequence reflection has students performing a mathematical action. They then observe a mathematical consequence. We ask questions. What did you observe? What changes? What stays the same? And we ask students to reflect on the result and reason about the underlying mathematical concepts. With GeoGebra, we can do our mathematical actions. We can create a graph. We can use a slider to manipulate that graph dynamically. We can perform computations. We can drag a geometric figure. We can do different transformations. All of these are different types of mathematical actions. The middle part, observing the consequence. The danger that we have if we just have students performing the action and observing the consequences, we need questions, reflective questions to give students an understanding of what's going on. I've had the experience, and I'm sure many of you have as well, where students remember that we did something on the technology. Oh, we did something on our calculators, or we did something on GeoGebra, or we did something on the smartboard, but they don't remember the math that we were trying to teach. So this engaging students in the action consequence reflection cycle, where we give them targeted questions to reflect and understand the mathematical concepts, that's going to make their learning more durable and deeper. So what kind of activities with technology are we going to use? I use sliders and dynamic elements to engage students in the action consequence environment. And I try to give students a pre-made file to allow them to focus on the implications rather than on the construction details. Now, of course, there are going to be situations where I want to do the math on the fly, like Ed did this morning, or there are situations like what Sarah was doing where we want students to perform the constructions themselves because it's part of our geometry curriculum. So pre-made files aren't always used, but they're a really nice help. So asking good questions. Try to create some questions that are going to give students an opportunity to think about the math that they are observing. What will happen if I do this? What must I change to make something happen? How is one thing affected by the other thing? What changes? What stays the same? When will something be true? Why does this happen? The last two items here, question shells, are asking students to formulate their own questions and giving them some question stems and shells for them to start to formulate their questions. And reversing order of representations. If we're always used to starting with an equation, then a graph, then a table of values, turn it around and deepen the students' learning in that way. Okay, I'm going to give this to you again at the end, but I'm going to take a look at a GeoGebra book. I'm going to do that in a minute. Okay, yeah, let's go to that now. So on GeoGebra, what you can do is you can go to geogebra.org/u/KDCamp, and that's the GeoGebra book that I am in. I'm going to put this in the chat. U for user, KD camp for me. And the first item there is an action consequence book. And as you've seen, a book is a collection of activities. And this activity collection now is up to, I think, 14 or 15 different activities because I keep adapting and changing. One of the things that we've talked about today in some other sessions, it's really important for you to, GeoGebra gives you the opportunity to copy somebody else's activity. And it's really important for, I think, for you to adapt the activity for your students. What worked for my students might not work exactly for your students. So adapt these as you go. Okay, so the first one that we're going to take a look at is a very basic, it's called power functions. Here is our handout, and the handout is asking students to graph the different functions. And you'll notice that in the GeoGebra activity, I have some of those same questions. Some of these activities were made way earlier on before we had question types that we could put into our activities. So I'm in the process of doing some updating, but if you decide to use this in your class, you would adapt it for yourself and make these interactive questions so your students could answer right within GeoGebra. So this activity is really just about end behavior. So we grab the slider. What happens as the power on X goes from 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10. And hopefully students are seeing the difference between U-shaped graphs and more S-shaped graphs. The questions are deliberately open-ended. What patterns do you observe? Asking them to think about what they see. As I'm going through this, I find it very interesting to bring the slider back down to 2 to 1. That's a surprising result for many students, but really that's the equation of a line, even though we're dealing with polynomials or monomials. And what happens when this slope is the exponent is 0? Well, now we have a straight line, y equals 1, the horizontal line. So there's all sorts of opportunities for students to make meaning here. You'll notice the third question down, what would be the shape of the graph if the exponent was 11? What would be the shape if the exponent was 12? And I've deliberately stopped my slider at 10 because I want students to make predictions here. There's also the opportunity to click on a negative leading coefficient. How are these results different from the ones with the positive leading coefficient? And all of my applets, I always have a refresh the construction icon so that students can do that. Let's take a look really quickly at the handout. This handout was designed for more graphing these items together. So sometimes when I'm doing this material, I decide instead, let me just get to this, I decide instead that I just want to do it on the graphing calculator. And so what would happen if I graphed x squared and then x to the 4th and then x to the 6th, all on the same graph? And this is an entirely different situation because now students get to see them all at the same time. And so my first question on the handout, I asked students, what do they observe? And my students observed things that I didn't necessarily intend to be part of the lesson. If my intention was to talk about end behavior, whether both sides of the graph go up or one starts down and ends up, my students looking at this graph noticed that we had points in common, or that the graph got steeper as the power increased, or down between 0 and 1, the graph got flatter. And so these kinds of other noticings that students made, sometimes you'll have time to address them right in your lesson, but even if you don't, it's worth coming back to them. I like to think about it as taking the scenic route through the mathematics, and there's other wonderful math that might crop up because all of our math concepts are connected to other math concepts. So, don't be afraid to take the scenic route. And just to show you what else we can do here, if we really wanted to examine what's going on in this graph, we can take each of these values and we can put them in each of these functions, and put them into a table of values. And let's start our table of values. Let's leave it where it is at 2. Let's end value at 5. Just by clicking on the 3 dots in the calculator suite, I can add my functions to the table of values. And so now let's take a look at this. We can see those points of intersection at 0 and 1 and -1 x values. We can also see what's happening with the y values. Students often describe the x squared to x to the 4th to x to the 6th as the graphs are getting skinnier. But really what's going on is the y values are getting bigger. And I really like to highlight that verticality of what's going on because we are exponentiating the x values so much more. We're getting higher verticals. And so this table of values gives another insight into the graph behavior. If we want to take a look at what's happening in between 0 and 1, I can click on my 3 dots near my x value. I'm going to start at 0. I'm going to end at 1. And this time I'm going to use a 0.1 step size. And now we can see that the in-between values reverse the y value behavior. The values in between 0 and 1 reverse the y value behavior because more exponentiation makes our y values smaller. So we get a numerical justification for the graphical impression that the graph is flatter. So this activity really has a lot of legs. You can do it in the GeoGebra book where, let me go back to that, where we're just manipulating the slider, or doing it in the calculator suite and gives us a different view of it. You'll notice on the handout, the paper handout that you're going to get, it's asking students to make predictions, making summaries, and the piece of the action consequence reflection cycle that is most important is that reflection piece. Without that piece, students might forget some of the math we're doing. And so in service of that reflection, you might have students working independently or in partners with this. But when the activity is over, it's really, really critical to summarize the activity for the class. And I don't mean necessarily the teacher does the summary, but that the class discusses the concepts that were in the lab activity. This allows you to clarify any misconceptions that might still be out there. It allows you as the teacher to make sure that your lesson objectives were actually learned. Perhaps some students really were focusing in on this flatter, skinnier, and missed the big picture of the end behavior that was my lesson goal. And like I said, this summarization doesn't have to happen by the teacher. It's even more powerful when it happens by the students. But that's a key part of the process that you're going to do. Okay, so now let's take a look at my next. There's many, many activities in this book, and I'm going to skip over some of them, but let's take a look at function transformations. Okay, and this function transformations activity is a classic, what do we do with a parent function when we have sliders A, H, and K? And so here we go. We have A is working a little bit like the one we just saw, where A is going to increase, it's going to multiply or stretch our vertical values, our Y values. What happens when A gets negative? What happens when H moves? H is the horizontal translation. What happens when K moves? And so the activity, the lab activity that students have, oh, excuse me, there are questions are down here. In the actual GeoGebra applet, I simply asked, how does the parameter A affect the graph? How does the parameter H affect the graph? How does the parameter K affect the graph? So that's a very straightforward, what are we going to do here? In the handout, it takes students through some more specific questions, not just what does A, H, and K do, but give a possible pair of equations for this function. So this is reversing our representations, making sure students apply the math. Number 5, how is the graph of the transformed function related to the original function? What is the same and different? And try different parent functions. So what's really nice about this is we can change this parent function here. We can make this x to the 3rd. See how that works? We can make it square root of x. And so students can take a look at all sorts of different versions of this: absolute value of x, sine of x, etc. Now, some of you may say, gee, I also want to include changing the coefficient of the x inside that function. It's often used parameter b. And what happens with the parameter b is that I've found it's the one that confuses students the most. It's the horizontal shrink or stretch, and it works in the opposite order to the vertical stretch and shrink. So that what I mean by that is that vertical stretch and shrink, as A gets bigger, we get a vertical stretch, and as A gets between 0 and 1, we get a vertical shrink. And the B values work in the opposite order. So I found my students get very confused with that. So that's why this particular functions transformations is only with A, H, and K. So to tease out what's going on with the B value, I've updated this for functions transformation 2. And so let's take this graph here. G of x equals 2 times x minus 1 squared. I want to compare that to the graph where the 2 is inside. And so what you have to do here is you have to input EQ1 of x equals 2x minus 1 squared. And nothing's going to happen until you check off this checkbox. And we can see that these graphs are completely different. The black graph is not in the same place as the red graph. It's not the same width or vertical stretch. And what I want to ask students about this is that what is this 2 in my new equation really doing? Well, that 2 is getting squared. So what I really need on my g of x is a 4. Let's see what happens when I change A to 4. Oops, it's not, doesn't want to go. That's okay. We can make it 4 in this box. Now the black and the red look like they have the same vertical stretch. Well, the other thing that's going on here is that the g function has been translated 1 to the right. This 1 is no longer 1 to the right because my 2 has been factored out. What I usually say to my students, I'm going to take that same function, but I'm going to factor the 2 out. 2 times x minus half, close parentheses, and then square it. Okay, and to see that the x translation, the h parameter really needs to be 1/2 to get those to be the same. So this additional equation, equation 1 of x, allows us to work with that idea of the b parameter. Let me just do one more thing here. The idea of ignoring the b parameter works great for quadratics. It works great for quadratics and absolute value, but once you get into square root of x, okay, once you get into square root of x, you have a situation where having a negative value or a b parameter can't be factored out like we did with the quadratic. So if I do square root of, well, sometimes it can. If I do square root of 4x, that one can be factored out. And that would give me an a value of 2, because I can take the square root and pull it outside and get my horizontal translation to 0. Oops. Okay, and they would be the same. But what I can't do is, what if I have a negative underneath the square root in that radicand? Square root of negative x minus 2. What's going on there? That's going to be a reflection in the x direction, and that you cannot recreate by sort of pulling or factoring out the b out of the function and combining it with the a. So there's a lot of detail that I might want to work on with my students with this idea of b. For the most part, with Algebra 2 students, Algebra 1 students, I'm just going to stick with A, H, and K in my function transformations 1, but function transformations 2 gives us an opportunity to show that input equation. Okay, let's change gears a little bit. Let's take a look at invariants. And invariants are something about a mathematical situation that stays the same while other parts of a situation change. It might be a measurement, a calculation, a slope, or a location. And so what I love, this is one of my favorite activities. I think I've done this activity on every geometry technology there is. Interior and exterior angles of a triangle. And, you know, students learn this, and it's not hard for us to just teach them the rules for angles of a triangle and what they add up to. But when you do something dynamically, where a student has an opportunity to observe what's happening and reflect on that math and make the meaning for themselves, their learning is much more durable and long-lived. Okay, so the instructions are move point B to change the shape of the triangle. And what dynamic geometry affords us is the idea that we're not just constructing one triangle, we're constructing infinitely many. So my mantra is drag and move whenever we're doing geometry, dynamic geometry. So the first question on the handout, and I actually need to add it onto the GeoGebra activity before the chart, is move point B to change the triangle shape. What do you notice about the angle measures? Because I want students to think about it before they do anything with the math. It's just the same way that when we have students who see a word problem and they just start adding and multiplying the numbers of the word problem without reading, I want students to make some observations. Do they notice that one of the numbers is always obtuse? Or, you know, can we ever get the outside angle to be acute? What do we want them to notice? I do want them to record several sets of measurements in the chart. And what do you notice about the angle measures as the shape of the triangle changes? Students are going to, hopefully, I usually do this activity after we've learned about the sum of the 3 interior angles. So students can confirm that no matter what's happening, my sum of my 3 interior angles is going to add up to 180. But the next question is my favorite question. What other angle pairs would you like to add together? Because I don't want to tell students what to pay attention to. I want them to take a look. And my experience with this is that some students don't know what they want to add together. They've filled up their chart. They don't know what they want to add together. And ironically, sometimes it's the most capable students who are in the highest level math class who don't know what to do next because they haven't had a lot of experience. They've had a lot of experience with doing things correctly in math class, and they don't want to do things incorrectly. So they say to me, what should we do? And I've tried really hard when they get to this question, what other angle pairs would they like to add together? I don't tell them which ones. I say, take a look at your chart. Do you see any pairs in your chart that add up to interesting numbers? And so there's 2 different pairs that add up to interesting numbers. One of them is this adjacent interior and the exterior angle. And the other pair that adds up interestingly is the two remote interior angles. They add up to the exterior angle. So I try very hard not to give it away, but when we get to the point where they need hints, they can show the sets of angles to add together. And these sums are dynamic. So the three interior angles do add up to 180. The two remote interiors do add up to the exterior, and the adjacent interior and the exterior add up to 180. And so students on the handout have to make a generalization summary. How is the exterior angle BCD related to the other angles, and explain. And the last thing or the second to last thing that's on this handout is to list the measures of the exterior angles of all the exterior angles of the triangle. And this originally happened because I realized that students working with technology work at different speeds. So I have fast finishers who back in the day, we would be in the computer lab, they'd be off looking at the internet, they'd be off task, or they'd be disrupting other groups. So one of the things that I always try to include in an activity, if I can, is what are some additional extensions for fast finishers? And the other thing you can do to keep kids sort of all working at a pace that is reasonable is you give kids groups. And one of the things I learned is you give two students one piece of technology so that they have to share the work, they have to talk to each other. The first part of the activity, student A is going to be pressing the buttons or moving the mouse, and then switch to student B. So there's a bunch of different things that you can do to enable students to talk together and to enable the conversation to happen. So the three exterior angles, they are going to add up to 360, and that's another interesting and wonderful result. And finally, on the handout, ask students to predict what's going to happen, apply their knowledge, and then create and solve their own, or some other ways that you can build this understanding. Okay, moving along, my next one I want to share with you is right triangle ratios. And this is a, pretty familiar idea of what we're doing with the ratios in a right triangle. But before we even name them as sine, cosine, and tangent, I want students to work with moving and observing. So if we grab and move point F, what measures are staying the same, what measures are changing, and pretty much everything is changing. If I'm moving point F, the only thing that doesn't change is side AC, but all my ratios are changing. Okay, the triangles that I'm creating are not similar. They are right triangles, but they are not similar to each other. The second part says, what about moving point C? Well, now the side lengths are changing, but none of my ratios are. I made the deliberate decision to move point F first because I wanted students to realize that this was a dynamic diagram. If they just started by moving point C, which is sort of the meat of the sine, cosine, tangent ratios, they may not realize that these three gray boxes are also dynamic. And those indeed are similar triangles. And the handout goes farther than the GeoGebra activity does. The handout builds this whole idea of sine, cosine, tangent. Make these ratios using the ideas or the words measure of the hypotenuse, measure of the adjacent leg, measure of the opposite leg, and summarizing for students. So those activities give you a little taste of some invariants. I'm going to shift gears to another category of these activities, and that's the idea of these activities as visualizers. And one of my favorite visualizers was created by my good friend, Tim Brzezinski. Tim, I don't know if you're on this, but lots of people have talked about Tim today. Tim created this activity to build understanding of that issue where you have an altitude to the hypotenuse of a right triangle. And this is one of those things that we can teach the students the relationship, but it's very hard for them to grasp it sort of in their bones, understand what's going on. And it's really because it's all about similar triangles. And yes, it has to do with geometric means and proportions. But Tim created this where we are taking a look at where are the equal angles. And so you can see that the red angle from the bottom left corner is also part of the small green triangle. The blue angle from the bottom right corner is also part of that medium-sized triangle. And then we have all three triangles, which we're going to orient this way so we can see that we have all of our our congruent angles in the corresponding locations, and we get them to show up here and we get them to show up there. And so once I saw this visually, I decided that this is how I'm going to lead teaching on this. I'm not going to teach directly that geometric mean where the altitude is the geometric mean between the segments of the hypotenuse. Instead, I'm going to say, find your similar triangles, make a proportion with corresponding sides. Okay, another visualizer that I actually just created a couple weeks ago is zero and slope fractions. One of the places that I'm going to tell you you can find me is on my blog, and late January, I made this post dividing with zero, understanding zeros in fractions and slopes. And the issue that I was having was that students were mixing up what's going on with zero divided by a number and what's going on with a number divided by zero. My students knew that they're undefined or they're zero, but it was hard to say. And when we got into talking about slopes, we got into an issue where some teachers, a previous teacher had taught that when a vertical line has no slope. Well, no slope is confusing. Does that mean undefined slope, or no slope means it's zero? So anyway, let's take a look at the visualizer. And this visualizer here is having our slope be, having a fraction represented as slope, and I can draw a slope triangle to show what this does. And what we can do is we can see what happens with negative slopes, with positive slopes, and what happens when the numerator is zero. Well, I get my purple line, I get a horizontal line y equals 0. And the questions ask, what happens to the slope? What happens when the numerator is 0? On the handout, I ask students, can the equation of the line be put into slope-intercept form when the numerator of the slope is 0 or when the denominator of the slope is 0? So yes, we can create slope-intercept form when we have a numerator of 0, but what about a denominator of 0? Denominator of 0, my purple line is gone. The symbol that we've got up here is y equals infinity times x. It cannot be put there. This is an undefined situation. And this visualizer really helped my students thinking about what to do when they have a 0 in their fraction. Okay, another new one that I have just been working on is an old favorite of mine, which is the idea of the Pythagorean theorem. And kids know the Pythagorean theorem. We have lots of great ways to teach it, but I was really interested in the converse of the Pythagorean theorem, where we say if a triangle meets the Pythagorean theorem, then it is a right triangle. But I also cared about what if it didn't meet the requirements of a Pythagorean theorem? What if c squared was greater than a squared plus b squared? What if c squared is smaller than a squared plus b squared? So grab and move one of the large blue points, and both this point and this point are available for students. And the important thing is that we do need C to be the largest value. So this long side of 8.3, that has C being the largest value. Once again, there is a chart for students to fill out. Do any of your triangles meet the requirements of the Pythagorean theorem? And what do you notice we're in triangles where c squared is less than a squared plus b squared and greater than a squared plus b squared? So here's one where c squared is less, and here's one where c squared is greater. And students can come to the conclusion that when c squared is greater, I like to think about it as a rubber band. My right triangle got opened even bigger. My hypotenuse was a rubber band. It got bigger, and my angle is now obtuse. But if I squeeze it in smaller, my angle is acute. And so students on the handout, again, do the right triangles confirm it? What do you notice? Some textbooks have it in the other order where it's a squared plus b squared is less than c squared. By putting c squared first, I'm going to have a greater than situation being the obtuse triangles. And I'm doing that because that parallelism helps students understand it even better. I could do it the other direction, but it ends up in conflict. And why should I have students remembering that something is backwards? Finally, on the handout, apply the math, create your own. And number 14 here, what happens if you try to make a triangle with sides 4, 7, and 11, or 4, 7, and 12? Gee, I wonder what happens. Let me go with 4 here. And let me try and make this 7. Well, gee, can I make the bigger side 12 or 11? Guess what? I can't, because it's going to make a straight line, or it's going to not have enough length in the two sides to meet the third largest side. That's the triangle inequality requirement. Okay, we're very close to running out of time. I want to show you one last idea, and that is that don't forget about being able to do some math on the fly. The CAS calculator in GeoGebra is pretty amazing, and I use that to do exponent laws and learning about exponents and simplifying radicals. So exponent laws, what happens if I do x squared times x to the third? This is still an action consequence reflection activity because students aren't doing this math yet. They're having the calculator do it for them. X squared times x to the fourth is x to the sixth. X squared times x to the fifth is x to the seventh. And we can even do x to the m times x to the n. And it's going to show us that we're going to add up those exponents. So instead of just teaching the students the exponent rules, we can have them experience what's happening with the CAS calculator. Very quickly, we can have students take a look at exponents themselves numerically. What if I do, what if I do 2 cubed, then 2 squared, then 2 to the first, and then 2 to the 0. So to build the understanding of 0 exponents, I would ask students what's happening to the power. The exponent is decreasing by 2, and what's happening to the result? We are dividing by 2. So what do we expect? 2 to the negative 1 is 1/2. So now we have an understanding of negative exponents based on that pattern of subtracting 1 from the exponent and dividing the result by that base. The last thing on developing understanding with CAS, I got this idea from Steve Phelps. Using the CAS calculator to simplify these radicals in order. What happens? Why does this happen? Use the factor command to elucidate that. Okay, we are rapidly running out of time, so I don't have time to show you that, but let me get back to my PowerPoint just to give you the details that you need on me. Okay, the GeoGebra book you can find at geogebra.org/u/kbcamp, the Dropbox folder. And how you can find me, I'm going to put all this in the chat just to finish up. You can find me at karen.camp@gmail.com. I'm on Twitter at KarenCamp, and my blog is at karendcamp.wordpress.com. I'm putting the Dropbox folder into the chat right now. Hopefully it goes. Yep, there we go. And the GeoGebra book, you can find it right from that Dropbox folder. And my Gmail is karen.camp@gmail.com. I really appreciate everybody spending time with me today. That went
Wonderful.
really,
Thank
really
you so
fast.
much, Karen. So thank you so much. So we will upgrade also your page for the conference at geogebra.org with some of the information. Okay, as a profile, definitely. Wonderful. Thank you so much for so interesting and example, an interesting talk and examples from and ideas about teaching. Thank you so much.
Thank you, Kasia, for having me.
Thank you. So now we are finishing. Yes, I think you Karen, you have to click the button, or maybe I can click the button.
Okay, you guys can find me on Twitter, email me, or see me in the next session. Looking forward to the next one.
Absolutely. Thank you so much. Thank you. And let's finish and go to the next in a moment.